Today we are going to start with singularities. Okay, so what are singularities? So singularities are like going to some special points, to be some special points. So our function is going to be holomorphic except at those special points. Okay, so of course we are not going to study singularities, in a bulk, and especially we are going to be interested about singularities which are isolated. Okay, so there goes the definition. First definition, yeah, isolated singularity. Okay, so especially what I'm trying to say here is that our singularities are going to be isolated points. Okay, so in the set of complex plane, so a function f has an isolated singularity at some alpha in C if there exists R positive such that F is holomorphic on, let's say, B alpha R minus alpha. So yeah, am I audible? All of you can hear, right?
Yes.
Yeah, okay. Yes, Sita, it seems I am audible. So here, that's my definition that I have, so it's for Jatin also, it's no voice. Hello, all of you hear me?
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, fine. So, so I have. So, what do I mean by a singularity? So, it or an isolated singularity. An isolated singularity is a point alpha such that I will have some neighborhood, deleted neighborhood of that point, where my function is going to be holomorphic, but not holomorphic at alpha. Okay. So, such points are going to be called isolated singularity. Okay. So, therefore, it's like that I have a function and it's going to be holomorphic in um, some deleted neighborhood around a point, and at that point the function is not holomorphic. Okay, so uh, clearly from this it should be clear because of Morera's theorem that if alpha is an isolated singularity of f, then f must be discontinuous. Like you can define some value, like whatever, let's say my function, you can give some value at alpha, but the point is that it is discontinuous at alpha. If it is defined there, then the function must be discontinuous. Okay, at alpha. Because if it would have been continuous and in a neighborhood, if the function is holomorphic, then by Morera's theorem, I will get that the function will be holomorphic there. Okay, so is it clear what I'm trying to say? Yeah. Yes.
Yes.
So all of you agree that the function must be discontinuous at alpha. Yeah.
Yes, sir.
It is defined there. It must be discontinuous. Okay. So let us see some example. The one which is very common. So f of z is equal to 1 over z, for example. I can take this one. Okay. So this has an isolated singularity. Tell me where?
At
At 0.
At 0. So that's clear, right? Because we know that this function is holomorphic everywhere in complex plane except at z equal to 0, right? Okay. So now that I have told you about isolated singularity, and so again some messages. Okay, so now that I have told you, Sita says again I am not audible. I don't know what is going on today. But others can hear me, right? Shita, why don't you go out of the meeting and join again? Something is wrong today. So is my screen visible?
Yes.
Yes, sir.
So this one you agree that this is an isolated singularity f of z equal to 1 over z has an isolated singularity at 0. Okay, fine. Now, of course, now that I have told you about isolated singularity, so you can clearly ask me that what if there is a meaning of let's say non-isolated singularities. Okay, so for example, I can give you such kind of um, scenarios. So non-isolated singularities. So there will be two types of that. So what are the types? So two types. So let's say type 1. So this will be such that the function cannot be. So the singular point is a one point, but the function cannot be made holomorphic around that point. Made holomorphic in a neighborhood of the singularity. Okay, so there were two things. Of course, existence of this R, which is going to kind of, as I was telling you, it's going to isolate this particular point from all other points. Okay, like other possible singular points and all that. And also the fact is that my function needs to be holomorphic in such a ball. So it might be possible that I'm not able to make my function holomorphic in a neighborhood of that singularity. Okay, so then we will call it a non-isolated singularity. So if I have to give you an example, then for example, if you take log z, so log z, we have seen clearly that this is not continuous at z equal to 0, and this one has non-isolated singularity at 0. Okay, because for example, you have seen that there is no way I can make logarithm, forget holomorphic, but even a continuous function in a disk around 0, right? We had to remove one line starting from 0, starting from origin. We had to remove one line to make our logarithm function to be even continuous. Like even if we do not bother about holomorphicity and level of continuity itself, it's not possible, right? So therefore, although this singular point, like for logarithm, the problematic point is only one point, which is 0. But even if the problematic point is an isolated point, just one single point, still in a neighborhood of that point, I cannot make my function to be holomorphic. Clear? So this is one of the cases which we are going to avoid. We are not going to study non-isolated singularities, but I'm just telling you the kind of problems one might have. So for example, we might not be able to have uh, a disk around that point where the function is holomorphic. Let's say not at that point, but so this kind of things can go wrong, and those are put as non-isolated singularity. And what is type 2? Type 2 is clear, it's clear from the kind of definition. So I'm going to take something opposite of isolated. So that means the singularities might have a limit point. Okay, so limit point of or the singularities might have a limit point. Singularities might have a limit point. Okay, so for example, you can take this function tan of 1 upon z. Okay, so this one at z equal to 0, this one is a non-isolated singularity. Has non-isolated singularity. Okay, so why? Because for example, I can take Zn equal to, let's say, pi by 2 plus n pi inverse of that. So this sequence of points are those where cosine is going to vanish, like cosine of 1 over z is going to vanish. So therefore tan is going to have a problem. So and clearly this Zn goes to 0, right? So Zn goes to 0 as n tends to infinity. So I can have this kind of scenario as well. Okay, so it's clear what are like non-isolated singularities can be. So remember that isolated singularities means we have, of course, the points are going to be, the problematic points are going to be isolated, that we understand, and also the fact that the function will be holomorphic in a deleted neighborhood around that point. Okay, so except for that point, we will have no trouble. Okay, so now so therefore what we are going to do, we are going to focus on this isolated singularities, okay, from now onwards. So we focus on isolated singularities. Okay, so there will be several types of isolated singularities. We are going to begin with one of them. Okay, so as I said, here I told you that if a point is an isolated singularity, so the function must be discontinuous at that particular point. And if, for example, I have a singularity where, let's say, I can in fact amend this defect, in the sense, suppose my function is discontinuous, that is given. So I have a function which is defined, and let's say it's discontinuous there. Then what I can do is that I can redefine my function at that point in such a way that the function becomes, let's say, continuous or holomorphic. Then that kind of singularity is going to be called removable singularity. Okay, so that's the first kind. So definition, removable singularity. So this you must be very familiar, because in real analysis you must have studied removable discontinuity, right? Yeah.
Yes, sir.
So that means,
Yes.
like, we were having limits at that point existing, except that the limit was not same as the functional value. Okay, so what you did, you had put that functional value there, like whatever the limit, you changed your functional value to be that limiting value, and then it becomes continuous. So exactly in the same spirit, we are going to have this removable singularity. So an isolated singularity alpha of f is called removable singularity of f if there is a holomorphic function g in a neighborhood of alpha, say b alpha r. So this, or let's say b alpha delta. So this delta could be different, such that your g z is equal to f of z for all z in b alpha delta minus alpha. Okay, So that means what I'm saying is that it's like I am having a holomorphic function in some ball centered at alpha in the whole ball, and that function matches our original function for all the points except z equal to alpha. So if that happens, then we will say that my point is a removable singularity. Is the definition clear? Yeah.
Yes, sir.
One point will be called a removable singularity. So that means I can remove the singularity, right? So that means I can, have the same means like at that point I can do some arrangement and make my function holomorphic. So that is what that is what precisely is going on. And okay, so exactly I'm saying that in a neighborhood I have a new function which is holomorphic, and it matches with the old function in that in the deleted neighborhood when you remove alpha. Okay, so let me give you an example. So for example, if I take f of z is equal to, let's say, sine z upon z for z not equal to 0 and 0 for z equal to 0. So let us say this is my function. Okay, so now this function has a removable singularity at 0. Okay, so why? Because I can take my function g, which is sine z upon z for z not equal to 0 and 1 for z equal to 0. Okay, now this function, can you tell me why this function would be holomorphic at z equal to 0? Yeah, why is it holomorphic at z equal to 0?
Yes, sir. Because it is only problematic at z equals to 0, and now it is continuous.
Yeah, so now it is continuous. So therefore, so once it is continuous, then what means, how do you get that this is holomorphic?
Morality.
Yeah, okay, so exactly that is the word I wanted to hear. So clearly, so means this one I have defined in such a way because I know limit z tends to 0 sine z upon z that goes to 1. Okay, so therefore I can, for example, show. So I take g like this. Note g is continuous at z equal to 0. So I have defined this value at z equal to 0 in such a way that g becomes continuous, and of course g was anyway holomorphic. Um, g is holomorphic on c minus 0, that was already there. So by Monera's theorem, we get, or corollary of Monera's theorem. Monera's theorem, we get g is holomorphic on c. Okay, so therefore what we see is that this new function g, which agrees with our function old function f for z not equal to 0, and g has become uh, holomorphic. Okay, so therefore z equal to 0 will be called a removable singularity of our function f. Okay. So is this clear?
Yes, sir.
Okay, so next comes the other definition, another type of singularity, which is called the polar singularity. Okay, so what is polar singularity? So if you remember, here you see, in some sense, of course, this limit that existed, that in some way says that okay, the function was actually bounded in that point where there was a problem. Okay, so now I can have points where for example, if I take situations like 1 upon z, then clearly I cannot assign any value at z equal to 0 and make it continuous at that point, right? So the following category is going to address those kind of singularities. So an isolated singularity alpha of f is called polar singularity. So when will I call it a polar singularity? If in a deleted neighborhood alpha neighborhood b alpha, let's say delta minus alpha, we can write f of z as g of z upon h of z, where gh belongs to holomorphic b alpha delta. So that means g and h are holomorphic functions on b alpha delta, such that I have the following condition: g alpha is not equal to 0, h alpha is equal to 0. Okay, so if I have this kind of a scenario, then I will call my singularity to be a polar singularity. Okay, so often we have seen that just because the denominator is vanishing, we cannot get our function to be holomorphic. So those kind of singularities will be called polar singularity. Okay, so that means what I am saying here, in a deleted neighborhood of my point, my function will be ratio of two holomorphic function, where the numerator does not vanish at alpha, but the denominator vanishes at alpha. Okay, so as an example, of course, like I told you, I'm going to expand or I'm going to general like treat the case f of z equal to 1 over z. So let us take that as an example. So this has polar singularity at z equal to 0. Okay, sure, is it clear? So clearly the numerator and the denominator, you can see the numerator is 1, which is constant function, so it's holomorphic. Denominator is z, which is again holomorphic function. 1 does not vanish at z equal to 0, z vanishes at z equal to 0, so therefore this has a polar singularity at 0. Let me just write 0. Clear? Yes? Is the definition and example clear?
Yes.
Yes.
Okay, so next comes the last category, which are called the essential singularities. Singularity. Okay, so what's an essential singularity? So an essential singularity is going to be one which is neither removable nor pole. Okay, so an isolated singularity alpha of f is said to be an essential singularity if it is neither removable nor polar. Okay, so if it is neither of these two, then we will call it an essential singularity. Okay, so later you will soon see the kind of I will give you some characterization of our singularities, like in terms of growth of the function, and then you will notice that exactly like when we think of our removable singularity, we have certain property of our function. When we think of polar singularity, then we our function will have certain property as we approach the singular point, and exact essential singularity captures exactly the remaining cases. Okay, so it will be very soon clear what do I mean by all this once we do this equivalent characterizations. Okay, so at this moment let me just tell you one example. We will come back to this and of course justify the example later. Okay, so an example here is exponential of 1 over z. Okay, so this one has an essential singularity at 0. Okay, so this is what we have, and we are going to show it later. Okay? Of course, as I said, I at this moment I don't have tools to show that this is not removable or not polar, but we are going to establish an alternate characterization of these various types of singularities, and that will be good enough to show that this is essential singularity. Okay, and in fact, we are going to do it into two types of characterization. So at this moment, I am the first characterization that is going to come will be in terms of growth of the function around the singular point, and the next characterization that we are going to do will be in terms of what is called Laura expansion. Okay, so we will see that. So first of all, let us try to do this one in terms of, as I said, bound of our function. Okay, so our growth of our function. Okay, so let's see. So characterization of singularities. Fine. So let's begin with removable singularity. Okay, so suppose I have removable singularity, then like what we were seeing in that case, that that means there exists a new function which was existing there, where which was holomorphic at that point, and all this. So that effectively tells you that your function is going to be bounded, right, in that neighborhood of that particular point. Okay, so or rather it's going to have a definite limit. Okay, so suppose f has an rather yeah, an isolated singularity at alpha, and suppose and limit z tends to alpha f of z exists. So suppose this happens. Okay, so I'm not talking about value at alpha, but I'm just saying the limit. Suppose it is an isolated singularity and I have that the limit exists. Okay, so then clearly you can see then f has a removable singularity at alpha, right? That's clear because if this limit value is equal to a, for instance, then I will define a new function. So if limit z tends to alpha f of z is equal to a, we can define exactly like in the example of sine z upon z, whatever we have done. Exactly we are going to do that. G of z is going to be f of z for z not equal to alpha, and a for z equal to alpha. So I can define it like this, and then g is going to be holomorphic in a dedicated neighborhood of alpha, and is going to be continuous at alpha, and therefore it's going to be holomorphic in the whole neighborhood of alpha. Okay, so exactly what I had done it for sine z upon z, same thing. In a more general framework, if I write like this, I will get this alpha is a removable singularity. So alpha is a removable singularity. All of you agree to this?
Yes, sir.
Yeah. Okay, so therefore the limit will exist. So if the limit exists, then it's going to be a removable singularity, and of course if it is a removable singularity, already there is a holomorphic function, so the limit will anyway exist. Okay, so but now what happens is that often it might be complicated to find the limit explicitly. Okay, so it might be a little bit complicated to find the limit explicitly. Instead of that, we can somehow, for example, to show that something has a limit is stronger than just saying that the something is bounded, right? But I was trying to tell you exactly that we need to look at how the function behaves around that point. So for example, if my function is bounded in that neighborhood of the point, then can I say that okay, I will get this removable singularity. Okay, so that is precisely the thing that we are going to do. So here comes the theorem. As I said, since calculating explicitly limit of z tends to alpha f of z might be difficult, we will consider this particular characterization. Alpha is an isolated singularity if and only if limit z tends to alpha. Previously we had f of z. This time I am saying z minus alpha into f of z is equal to 0. Okay, so this is what the theorem that we are going to prove. And as a remark, what I can say is that why this is a more useful criteria, because for example, to show limit z tends to alpha f of z, sorry, z minus alpha into f of z is equal to 0, all we need is to show f is bounded in a neighborhood of alpha. Do you see this? Yeah. So really I don't have to say existence, or I don't have to show existence of my limit at limit of my function f of z at z equal to alpha. Instead, if I can show that my function f of z is bounded in a neighborhood around alpha, that would be good enough. Already there is this z minus alpha factor is there, which is going to take my function to 0. All of you agree to this?
Yes.
Okay. Therefore, this particular formulation is more useful. Okay, so let's see the proof. So the proof is nothing, means it's not much difficult. So clearly so means, for example, proof. So if I take alpha to be a removable singularity, then this is anyway triviality. Okay, so if alpha is a removable singularity, let's say this is a removable singularity, so then there exists delta positive and such that, and G in holomorphic B alpha delta such that f of z is equal to g of z for all z in B alpha delta minus alpha. So this is what I have. Okay, so now clearly limit z tends to alpha, um, z minus alpha into g of z. If I calculate this limit, this is going to be 0, because this is just going to be both these two functions are continuous, so I can product limit of the product is product of the limits, so therefore this limit is equal to 0. Okay, and therefore this clearly implies, because when we take limit as z tends to alpha, we are anyway not interested in the value at exactly at alpha, right? We are rather interested value of the function around alpha. So, and around alpha, I know g is same as f, so this is equal to 0 as well. Okay, so if alpha is a removable singularity, already we can clearly see that this limit is going to be equal to 0. Fine, all of you agree to this? Okay, fine. Now that I have this, so I need to prove the converse, that I am going to assume that this is equal to 0, and thereby I have to show what? I have to show that alpha is a removable singularity. Okay, fine, let's do that as well. So suppose, suppose limit z tends to alpha, z minus alpha into f of z is equal to 0. So I'm supposing this. Now I'm going to define a new function. Okay, so and let's see what it is coming out to be. So define, once I have this limit, I can define this function h of z, which is equal to z minus alpha f of z for z not equal to alpha and 0 for z equal to alpha. Okay, I'm defining this function. So what do you think? What can I say about this new function h of z?
Continuous.
Holomorphic.
Continuous holomorphic.
Yeah, in fact, holomorphic. So H is holomorphic on B alpha delta minus alpha and continuous at alpha. So H is actually holomorphic on B alpha delta. Okay, so we have so far seen already application so many times application of this kind of trick. Okay, great. So now that I have this, what am I going to do? I am going to construct a new function. So you remember, I need to go to G. Okay, so G is like say I need to go to F. This H is not equal to F. Okay, so this H is some Z minus alpha times F. I need to go to F. So what I do is that I can do the following. So anyway, H at alpha is 0, right? So if I divide H by Z minus alpha, this is what is going to give me F. So define, exactly let us do that. Define G of Z equal to in this way. H of Z minus H of alpha. H of alpha is anyway 0, doesn't matter, but let me write in this form. For Z not equal to alpha and H, remember it's holomorphic, H prime alpha for Z equal to alpha. So can you tell me about this function? What can I say about this G now, this time? Yeah, what is this G?
Holomorphic at alpha.
Again holomorphic.
Again, holomorphic, right? Exactly this we have seen already so many times.
Yes.
Function, this function G is also holomorphic on B alpha delta. Okay, so exactly from the same principle, it's going to be continuous at alpha, and then I'm going to get exactly, or you have seen all these like satisfying integral theorem and all that, rectangle theorem, all this. So this function is also holomorphic. Now h of alpha is 0. What? H of alpha equal to 0. So that means what is g of z? If I take z not equal to alpha, can you tell me what is g of z?
F of Z.
This is exactly f of z if z is not equal to alpha. And you agreed that G is holomorphic on B alpha delta, and whenever Z is not equal to alpha, Gz is equal to f of z. So that implies alpha is a removable singularity of f. Clear to all of you?
Yes.
So therefore what I see is that a characterization coming out from here is that I have an isolated singularity if and only if the limit z minus alpha f of z is equal to 0, and that in fact I can translate to saying that f of z is bounded in a neighborhood of alpha, because if f of z is bounded in a neighborhood of alpha, then z minus alpha times f of z is going to be equal to 0, and hence alpha will be an isolated singularity. And if alpha is an isolated singularity anyway, therefore there is a holomorphic function matching with the values of f around alpha. So therefore automatically f is going to be bounded in a neighborhood around alpha. Okay, so therefore this, yeah, yes, Abhishek.
So actually, 1 over Z has a pole singularity.
Hmm.
Okay, and this one is also the isolated singularity. Zero is only isolated point.
Yeah,
So we have just proved the removal singularity.
yeah, so 1 over z is not removable singularity, right?
So,
Okay.
but the problem statement is saying that isolated singularity. That's why.
Sorry, thank you. I meant removable singularity. Thank you. So alpha is a removable singularity. Sorry. Thank you for pointing out. Alpha is a removable singularity if and only if this happens. Yes, of course. I was talking about removable, right? In the statement, I that was a typo. Thank
Yes.
you for pointing out. Yeah. So it's a removable singularity means I'm going to have this function to be bounded. Of course, I started by saying I'm going to characterize removable singularity. Okay, so therefore, as I said, we can reinterpret this statement as follows. Alpha is a removable singularity of f if and only if f is bounded in a neighborhood of. Fine, clear to all of you? This one. Okay, next comes the polar singularity. Okay, so of course now once you think of something which is bounded, it's going to give you removable singularity. Now if your function is not bounded in a neighborhood, okay, here I can have two kind of scenarios. One, which is that I am going to have a definite limit at that point, which is infinity when I take absolute value, or we might not have any definite limit. Okay, so the polar singularity falls in the category where I am going to have a definite limit which is infinity, like exactly like 1 over z. If z tends to infinity when you take absolute value, 1 over z is going to tend to infinity. So exactly that is what is going to happen. So polar singularity, in that case we have the theorem that let alpha be an isolated singularity of f, then alpha is a polar singularity if and only if limit z tends to alpha mod of f of z is equal to plus infinity. Okay, so of course my function could be unbounded near a point by, you know, with several possibilities. Okay, one of the possibility is that no matter which way you approach your alpha, mod of f of z is going to have a definite limit, and that limit is plus infinity. If that happens, then we will get that our function is going to have a polar singularity. Okay, so the moment I am able to prove this, I will automatically have, you know, a characterization for the uh, essential singularity. Okay, so therefore, like in case of singularities, the way I have defined, you can also remember it in terms of three ways. Like there are going to be three possible, you know, things. So one is that the function could be bounded. Another one is that in the unbounded segment, your function in absolute value will have a definitive property that it's going to go to plus infinity in absolute value, or it might so happen that your function, some of the points might go to plus infinity, some of the points might remain bounded and all that. Okay, so that will be essential singularity. So let's first complete proof of this theorem. Okay, so what do I want to say? I want to say that if my function has a polar singularity, then the limit z tends to alpha mod of f of z is plus infinity, and of course the vice versa. So let's do that. So let alpha be a polar singularity. So let's assume this. Then, of course, by definition, in a deleted neighborhood, in deleted neighborhood, let's say b alpha r minus alpha, we can write f of z is equal to g of z divided by h of z. So suppose I can do that, and of course g and h are holomorphic. B alpha r. I also have the property that g of alpha not equal to 0, h of alpha equal to 0. So I have this property. Okay, now g and h are holomorphic on b alpha r, and so what I can do is that, of course, it's a holomorphic function given in an open set. So if necessary, I can, for example, just imagine in place of r, I can substitute r by 2, and I can take the closed ball. So the closed ball, in that closed ball, my function is going to be holomorphic, or even so therefore continuous, so bounded and all that. So effectively what I can do is that I can choose r such that my function g and h are even bounded on b alpha r. Okay, so if necessary, by reducing r, we can make sure g and h are holomorphic, are bounded, sorry, on b alpha r. Okay, so if it is not bounded on b alpha r, you just imagine, replace r by 2. So the function is going to be anyway holomorphic on b alpha r, so that means it's going to be holomorphic in the closed ball b alpha r by 2. So therefore in particular continuous there. Okay, or rather continuous on this whole open wall. So in particular, if you take any compact sub balls, that is there also the function is going to be holomorphic, so therefore it's going to be sorry, continuous, so therefore it's going to be bounded. Okay, so I have that my function is bounded on this form. Fine. Okay, now I am given that g is not equal to 0, right? G alpha, given g alpha is not equal to 0, so that means what? I can say, for example, that exactly like when something is non-zero, you will be able to find small neighborhood where the functional value stays completely away from 0, right? And in fact, you can do better. So since given g of alpha is not equal to 0, there exists, I can say, let's say r1 positive, such that on b alpha r1, what I can do is that uh, we have mod of gz is strictly bigger than mod of g alpha divided by 2. Okay, so you just, this is just applying epsilon delta definition, and you take your delta to be mod of g alpha divided by 2. Okay, so then you will get some epsilon, yeah, yes, so sorry, yeah, you need to take some r1, so that is the delta, your epsilon is mod of g alpha by 2. Anyway, so applying epsilon delta definition, you can do this. So you get your mod of gz is strictly bigger than mod of g alpha divided by 2 for all the points in b alpha r1. Fine, all of you agree to this? Yes, agreed? Yes or no?
Yes, sir.
Okay, now on the other hand, what is given? It's given that my h vanishes at alpha, right? So what I can do is that, so also h of alpha is equal to 0. So that means what? So if I am given any positive integer, any positive integer n, then there exists some R2, again positive, such that on B alpha R2, what do we have? We have that mod of h of z is less than 1 over n. Okay, so I can take epsilon to be 1 over n and I can get this. Okay, great. I got this R1 and R2. Now, if R3 is equal to minimum of R1 and R2, then what do I get? Then on B alpha R3, we have mod of f of z, which is mod of g of z divided by mod of h of z. So which is mod of g of z divided by mod of h of z. So let's say minus alpha. I have this. So this is going to be bigger than. So this one is in the other way. So tell me n by 2 mod of g alpha. Okay. So that means what? Of course, g alpha is not equal to 0, and I have this n. So that means given any natural number, I can find out balls where mod of f of z is bigger than some constant times n, right? Some non-zero constant times n. Okay, so given any natural number, there exists R3 positive such that on B alpha R3 minus alpha, mod of h of f of z is bigger than some constant, which is a fixed constant times n. So this implies limit z tends to alpha, mod of f of z is equal to infinity. Clear to all of you? Okay, fine. So we clearly see that if it's a polar singularity, then I have no choice. I'll just have mod of f of z will tend to plus infinity as z tends to alpha. Okay, so now I need to show that if that happens, I will be able to say that my alpha is a polar singularity. Okay, so let's do that. So next let limit z tends to alpha, mod of f of z is equal to plus infinity. So that is what is given. We have to show that alpha is a polar singularity. Okay, so of course we had started with alpha, which is an isolated singularity. So that means what? So we know f is holomorphic in a deleted neighborhood, let's say b alpha r minus alpha. Okay, so deleted neighborhood of alpha. Okay, so in fact here of course my function is holomorphic, and at alpha I can see that the functional value is going to plus infinity. Okay, so in fact, so that means what? As you go close to alpha, your functional value is become in absolute value is becoming very large and large. Okay, so in fact we can choose some r positive in such a way that my function do not even vanish there. Okay, so choose are positive such that f has no zeros on b alpha r minus alpha. Can I do that? Yes or no? For example, since the limit is equal to infinity, so I can ensure that there will be some r positive, so that mod of f of z is bigger than 1 for all z in b alpha r minus alpha, right?
Yes, sir.
Yeah, so therefore in particular I can make sure that the function does not have any zero, because the limit is anyway plus infinity. Okay, fine. So I have this. Now once, why do I do this? It's natural when we are considering a function which is having no zero, the agenda would be to consider the reciprocal. Okay, so consider h of z is equal to 1 upon defined by 1 upon f of z on b alpha r minus alpha. Okay, so this does not have any singularity in this case because your denominator is non-vanishing, and we have already seen if the denominator is non-vanishing, reciprocal of your function is going to be holomorphic. Okay, so this function is holomorphic. Okay, since f is holomorphic on b alpha r minus alpha, and and f is non-zero, then we get h is holomorphic on b alpha r minus alpha. Fine. So this is what I am going to get. Okay. So now tell me what is like this function h is a holomorphic function on b alpha r minus alpha. Now can you tell me what is the behavior? What could be the behavior of h at the point alpha? Tell me, what do you think?
H goes to 0.
Yeah. Okay, so this is an easy exercise. I am not going to do it. If you wish, you can take any, for example, epsilon bigger than 0, and you can show that mod of f of z is less than epsilon for some in a neighborhood around alpha. Okay, so just use that mod of f of z is going to be bigger than 1 over epsilon. So since this mod of f of z is equal to plus infinity, we have limit z tends to alpha, mod of h of z is equal to 0. And if the limit of absolute value is equal to 0, this will of course imply limit z tends to alpha, h of z is equal to 0. Fine, all of you agree to this?
Yes,
Yeah.
sir.
So if we set h of alpha equal to 0, then h becomes a holomorphic function on B alpha R. All of you agree to this? Yeah,
Yes, sir.
fine. So now remember this H is a holomorphic function on B alpha R, and this vanishes at uh, alpha.
Alpha.
So what I can do, I can first of all write down a a power series expansion. Okay, so H has a power series expansion of the form summation n bigger than or equal to m a n z minus alpha power n. Now can you tell me what could be my m? Where? What could be my m? Can I say something about this m? It's an integer or non-negative integer. Can I say something more? Tell me, can I say something more about this m?
Greater than equal to 2.
No, greater than equal to 1. Not 2, right? Greater than equal to 1. That h of alpha is equal to 0, so the constant term must not be there, right? Right? M equal to 1 is good enough, no? To ensure that it vanishes. Yes or no?
Yes, sir.
Yeah.
Yes, sir.
So I get m is where m is bigger than or equal to 1. All of you agree to this? That my power series expansion will look like that? Yeah.
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
Here where am is not equal to 0 and let me bigger than equal to 1 and let me also put am is not equal to 0. So that means all which for which ans are 0, the initial ones I am going to throw them away and I am going to start from am, which is the first non-zero coefficient that appears in the power series expansion. So I'm going to keep it from that point onwards. Okay, so now what I do here is that I can rewrite, for example, from this I can take out some factor, let's say z minus alpha power n, and I can define a new function. Okay, so define h1 of z by summation n bigger than or equal to m a n z minus alpha power n minus m. Okay, so that's my new function h1 of z. I am defining it. Okay, so can you tell me where I can make sense of this function? Definitely, where can I make sense of this function? This is also given in terms of a power series, so where can I make sense of this function? So let me write this converges on b alpha r as, you can notice, a n x power n bigger than or equal to m and n bigger than or equal to m a n x power n minus m have the same radius of convergence. Right? This kind of observation we have seen already, isn't it? That even if you skip one term, you are still going to have the same radius of convergence, isn't it?
Yes.
Yes, sir.
Yes, sir.
So therefore, h1z makes sense for all z in b alpha r. Agreed?
Yes, sir.
Now tell me, what is h1 of alpha? What is h1 of alpha?
0.
No. Be careful. What I have done, carefully
Okay.
notice. This is equal to am, which is rather not equal to 0. So I have, what I have done in h1 effectively, I have take out the factor which was killing my, means which was making my function h to be having a 0 at alpha, right? Is it
Yes,
clear?
sir.
So therefore h1 of alpha is not equal to 0. So what now I am going to do, I am going to, of course, this function is non-zero at the point alpha, but it could have some other zeros. So let us first eliminate all of them. Okay, by already identity theorem, we know that zeros are isolated. So I can choose R1 positive such that h1 of z is not equal to 0 for all z in b alpha r1. Anyway, at alpha it is not equal to 0. So exactly in the same principle, like I can choose some epsilon delta also. In that manner also you can see that I will be able to find out some radius r1 where h1z is not equal to 0. Now what is f of z? Now f of z is 1 upon h of z. That is how I had defined h of z to be. So f of z is 1 upon h of z, and this guy is having 1 upon z minus alpha. Note that whatever I am doing, I am going to do it for z not equal to alpha. Okay, so this is power n h1 of z, and this I can write as 1 upon h1 of z divided by z minus alpha power n. Okay, and clearly, of course, now that h1 is not equal to 0, so 1 upon h1 is a holomorphic function. Clearly, the denominator vanishes at alpha, numerator does not vanish at alpha. Okay, so alpha is a polar singularity. Are we done? Yeah, is it clear to all of you? What I
Yes,
have?
sir.
Yeah, so effectively what I did, I just considered the reciprocal. I know since my function is going to plus infinity, the reciprocal is going to go to 0. Take out all the factors which are making it 0. Then you are going to left with a function which is not going to, which does not vanish at that point. So in a small neighborhood, you can invert your function. Okay, so this again, this is gone. This one is on B alpha R1. Okay, so on a small neighborhood, you can invert that function which is non-vanishing, and therefore I can write my function as ratio of two functions where the denominator is vanishing at alpha, numerator is not vanishing at alpha. Each of them are holomorphic. Okay, so therefore my function is becoming a, my point, the singularity is becoming a polar singularity. Okay, so here in fact, as a result of this proof, what you can see is that of course if your singularity is a polar singularity, you know that the denominator is going to vanish somewhere. Okay, and in fact this proof kind of suggests that if I have a polar singularity, okay, then so if alpha is a polar singularity at polar singularity of f, then if then there exists a natural number. So here natural number means bigger than or equal to 1. Natural number m bigger than or equal to 1 such that I can write f of z as g of z divided by z minus alpha power n in a deleted neighborhood of alpha where g is a holomorphic function, g of alpha not equal to 0. Okay, so g is a holomorphic function in that deleted neighborhood and g of alpha is not equal to 0. Okay, so this integer m is called the order of the pole, order of the pole at alpha. Okay, so you can also see the same order as the order of the 0 of 1 over f at alpha. Okay, so that's the same. So this order is nothing but the order of 0 of 1 over f at alpha. That's the same order. So whenever you have a polar singularity, you will be able to write down your function f of g of z as z minus alpha power m. So like even if we said in the definition that we can write it as g of z by h of z, where h of z is going, h of alpha is going to be 0 and g of alpha is not going to be 0. So from since h of alpha is equal to 0, you can write down a power series expansion of h of z at alpha and take out all the portions which are making at like which is giving the 0 at alpha, and then remaining once you take out that factor, whatever power series remains, that's going to be a non-zero power series, that's going to be a holomorphic function, that's going to define a holomorphic function, and it's going to be non-zero at alpha. And the moment it's not non-zero at alpha, you can just imagine the reciprocal function that's going to give you a holomorphic function in some neighborhood around alpha. So therefore effectively what you can do is that you can write your function f as some holomorphic function divided by only z minus alpha power m, okay, for some positive integer m, and that m is the order of the pole. Okay, so is this clear to all of you? Yeah.
Yes.
Okay, so once I have this, of course essential singularity was anyway defined singularity which is neither polar nor removable. So therefore, essential singularity is for them. The above two theorem is going to give me the following. The above two theorems give this. I can write this as a theorem, or you can call it a corollary. Let alpha be an isolated singularity of f, then alpha is an essential singularity of f if and only if there exists two sequences an bn converging to alpha as n tends to infinity, such that with f of n is bounded, or let me write such that is better, such that f of n is bounded and f of bn in absolute value goes to infinity as n tends to infinity. Okay, so essential singularity means you cannot really predict the behavior of the function as you go close to the point that you are interested in. That means it's not having a definite behavior, so of course it's not going to be bounded, and it's not also in absolute value, it's not also going to plus infinity. So there will be several occasions when it's going to come, means like it means like you will be able to find two sequences which are going to alpha, but their functional values are going to have two different behaviors. Yeah, so is it clear? If I have an essential singularity, then I will have these kind of two sequences. Yeah.
Yes, sir.
Yes.
So for example, if I, for example, I have f of an is bounded and an is tending to alpha. So clearly that tells you that alpha cannot be a polar singularity, right? Because if alpha is a polar singularity, then we know limit z tends to alpha, mod of f of z is infinity. So if an tends to alpha, then mod of f of an should tend to plus infinity. Similarly, if you consider this one, so that is going to give you that we have seen that if my function has to have a removable singularity, then the function needs to be bounded in a neighborhood of alpha, in some small neighborhood. But here I am getting that the functional value in absolute value is going to plus infinity, so that's not going to be and that's not going to be a removable singularity. So therefore, effectively, we only have essential singularity which is left. Okay, and of course, if it is an essential singularity, then it's neither pole nor removable. If it's not a pole, so that means what? You cannot, for example, so let me do this that part separately. Okay, so proof if there exists an such that n tends to infinity, sorry, n tends to alpha, and f of n is bounded, then f is not, sorry, then alpha is not a pole, if there exists bn such that bn tends to alpha and mod of f of bn tends to infinity, then alpha is not removable. So alpha must be essential. Okay, and conversely, if alpha is essential, so that implies what? F is alpha is not removable. So this implies F is not bounded around alpha. So this implies there exists Bn such that Bn tends to alpha and mod of f of Bn tends to plus infinity. Okay, so this is what I get, but alpha is also not polar singularity. So polar singularity means if and only if limit means limit z tends to alpha, mod of f of z goes to plus infinity. So if it is not a polar singularity, that means what? There will be a sequence which will tend to alpha, but absolute value is not going to go to plus infinity. It's polar singularity is not a polar. So there exists a sequence an such that an tends to alpha and mod of f of an is bounded. Okay, so therefore this is an easy corollary from the other two cases. Okay, so now that we have set up all this, we can prove the following statement. So as a corollary, we can get exponential of 1 upon z has an essential singularity at 0. Okay, so that means what? To show that a point of singularity, isolated singularity, is an essential singularity, what do I have to do? I have to find two sequences. Both of them are going to go to 0, but their behavior are going to be different, the functional values. That means one will go to plus infinity, like in absolute value, and another one is going to remain bounded. So can you quickly give me two such sequences?
1 by n and minus 1 by n.
No, it is going to be useful in this case. Tell me what is your, for example, give me an an so that f of an is bounded.
Minus 1 by n. Minus 1 by n.
Minus 1 by n.
Yes, sir.
This one. So you want to take, okay, so exponential, fine. Exponential of minus n, and this one is, therefore, tell me this is less than or equal to 1, right? I have this 0 less than this, less
Yes,
than
sir.
bounded. Now what is your bn?
1 by n.
Bn is 1 by n. So in that case, I have exponential of n, and that goes to plus infinity and tends to infinity, right? So therefore, clearly, you could give me two sequences which are going to have, like when I look at their functional values, they are going to have two different kind of behavior. Okay, so please remember the type of singularities in this way, that for the removable singularity, you are just going to have only bounded nature. For polar singularity, your function is not only going to be unbounded in a neighborhood of that point, but rather no matter what sequence you take which approaches to that point, the functional value of that sequence, when you take the absolute value, it should go to plus infinity. So therefore, it's not an oscillating limit. That limit might not exist as a real number, but nevertheless, when you take absolute value, that limit exists actually, like in the extended sense, in plus in. So the limit is going to be plus infinity. It will not be a finite limit, but it's going to be limit which is plus infinity. So I can definitely say what is the behavior of my function around that point. It's going to have, like it's going to go to plus infinity in absolute value. But if you have essential singularity, then you cannot say anything. So that means in neighborhood of my sequence or my point of singularity, I will have various different kind of behavior. My function could remain bounded for some sequence. My function could be could go to plus infinity for another sequence. So we will have various such possibilities. Okay. So this is what is the characterization of the essential singularity. Okay, so we will see some more, we will do some more study about these singularities, and there will be something very interesting which is called the LoRa expansion. Like we have written power series expansion for holomorphic function, we are going to do similar study for like functions with singularity. We will see what do we mean by LoRa expansion. It's going to be a similar kind of an expansion, and you will know from the LoRa expansion what exactly your function looks like and what it entails. Okay, so we will see that in the next class. Okay, thanks. I'll stop here. Are there any questions?